As a way to aid NASA's ongoing Artemis program and as a means of fulfilling the objective of the NASA Mines program, our research focuses on the development of a helical anchor-based thermoelectric generator that makes use of the Seebeck effect to generate power from an existing temperature differential. From early October to late March, my team investigated the feasibility of these power sources for use in a lunar environment, relying on experimental observation through both in-situ testing with a physically built testing rig as well as supplementary simulations done with CAD modeling through Fusion 360. The final design employs a top-down system of heat dissipation with a modified helical anchor meant to be embedded into lunar soil. This system would be able to act as both structural support and as a solid state and long-term power source without the need for frequent maintenance. This video's aim is to document the evolution of our design throughout the program, as well as to discuss specifics of the final design. Our original plan stemmed from the use of long-scale wiring with thermocouples through the use of the Seebeck effect to generate power with thermal gradients. The three main planned sources were sunlight, radioisotopes, and waste heat from other processes. Since then, we've begun focusing more on the waste heat aspect as well as providing just a more generalized function for an abstracted heat source. So in the beginning of the project, we noted that the Artemis mission is developing its lunar outpost, the Artemis Base Camp, by the rim of Shackleton crater, and that Shackleton had some pretty unique properties given its situation at the lunar South Pole. Like say, that Shackleton's rim is perpetually covered in sunlight while the inner walls of its crater are perpetually shadowed, that the average temperature of the South Pole surface is 260 degrees Kelvin while the inner walls sit at below 100 degrees Kelvin, and that the temperatures at the surface in this location don't vary by much, at least relative to the lunar equator. So what we planned was a long-scale circuit system that involved the hot plate of the thermoelectric generator sitting at the surface of the moon, and the cold plate being embedded within the inner walls of Shackleton. This was at the very least a 160-degree gradient, not taking into account other heat sources and only relying on the natural heating gradient of Shackleton. We thought of insulating the cold plate embedded in the walls with mica, so that way it would be able to effectively diffuse the heat generated from Joule heating as current passes through it and retain that temperature gradient. But a problem arose with our plan, namely that as one pushes the cold plate farther down in the crater, one gets a sharp increase in the electrical resistance of the metal conductor wire. We tried out a few different options, such as setting up TG panels like solar panels arranged as plates overlaying on a theoretical geodesic dome design for the base camp. But since that's more of a working theory and not a fully proposed design, we then looked for something more down to earth. So, we opted for a shorter scale design. After having a team-wide discussion with Dr. Led Klosky, a professor of civil engineering whose doctoral thesis was on the use of helical anchors for a long-term lunar surface environment, we decided to see if we could apply a helical anchor design and modify it to fit our parameters in our project. So we made a plan for a top-down system with a closed-tip helical anchor, where the bottom of the anchor served as the cold plate and the heat source would come from the top. The base of the anchor would be made with traditional steel, while parts of it for indirect contact with the lunar soil would be made with copper, which has a higher thermal conductivity. While we were experimenting with how to approach the mechanical design, we also had to look into how the logistics of the thermocouple circuitry would be applied. We also looked into ways to apply our design in conjunction with other processes, such as electrolysis and even power generation through solar energy. After finding conductor wiring with metal to be too variable to deal with, because of the way it increases electrical resistance with increasing temperature, we transitioned to a more streamlined method using semiconductor material. While this meant that the wiring would only reach a short depth, we found a way to extend that by applying solid metal to act as a mid-system heatsink embedded concentrically within the anchor. We then used multiple layered concentric metal cylinders to act as radiator fins in order to maximize our contact surface area with the soil. After more work, we were then able to come up with a design that we agreed upon. As this was an experimental project that required in-situ testing, we had to figure out how to approximate the lunar environment. This was done by creating a custom vacuum chamber that fit our design specifications using sheets of thick acrylic. We decided on 3 ceramic heat emitters to emit heat from above the surface as our heat source. Because lunar simulant was costly to purchase, especially with our scale, we we decided to use sand to approximate the lunar environment, as it was the closest enough readily available material to lunar soil in terms of thermal conductivity, abrasiveness, relative density, and other factors. Some more problems appeared along the way as we were designing, such as the use of a cooling system, the lack of commercial availability for circular TEGs, and others, which we resolved along the way. Because the soil subsurface would heat up gradually with the constant heat input, we used a pipe-based cooling system to wrap around the walls of the acrylic testing rig to approximate the, for our purposes at least, essentially limitless heat capacity of the lunar subsurface. Because circular-shaped TEGs were not commercially available, we instead sourced square, flat bulk TEGs and filled the exposed areas with a layer of insulation. However, the physical design was only half of it. We also had to take care of the less bulky aspects of the testing rig. While building, we also had to figure out how to collect our data from our experiments.
The general process for creating the code for measuring the temperature was really not that difficult. Luckily for me, most of the hard work had already been done by people who wrote the libraries, so I only had to figure out how to use the libraries. Again, that wasn't really too hard, and I was able to work out most of the kinks relatively quickly. The first task I had to tackle was figuring out how to communicate between the Arduino and the computer I was using to gather the data and write it to the disk. The general process would be to first read each sensor off of the Arduino, then send the data through the serial port to the computer, then then on the computer I would read the data from the serial port and write it to the disk for later processing, of course. To do this, I used Python on the computer and the PySerial library, and just regular Arduino code combined with the libraries that I used to read the sensors on the Arduino. The biggest problem that I encountered was actually saving the data collected by the computer. On the first run of the experiment, I realized I was collecting the data wrong. This means that the way the writing to the files worked meant that to actually save the file to the disk, you first have to close the file, right? So you open the file, write the data to the file, then you close it, and on close, it gets written to the disk. However, the way I was writing the program, the file never got closed. So what would happen was I would open the file, read from the sensors a bunch, write to the file, and then the file would never get closed, and the data would never get written to the disk, and it was all lost. This happened on the first run of the experiment, and which means all of the data from the first run we got was completely unusable. However, for the second two runs, I realized this problem after realizing that all my data for the first experiment was gone, and I managed to fix it by periodically closing and then reopening the file to append to the end. To measure data for the voltages, all I did was hook up a series of resistors to the TEG modules and read the voltage from them periodically with a voltmeter. Just go down to the experiment and write the voltage down. To process the data, I used the programming language R. To create the heat map, I first separated out a measurement from the a set of measurements from the height of from the point where the temperatures were at their maximums, so that the heat map would contain the most informational data. Then I melted these values into a long type data frame with R and used the temperature values in each column to create a matrix. Then I turned the matrix into a heat map and cut out each color value from the heat map and kind of overlaid each value with a gradient in Photoshop so that it would look at least slightly presentable. And I overlaid the gradient on top of a cross-section of a screenshot of the CAD model, and that was the hardest part of processing the data. The rest of it really wasn't too difficult. I just had to do graphs using the R library ggplot2, and all I had to do then was specify that I wanted to graph time versus each temperature value, and then combine those into a graph, and then combine the voltage into a graph and the wattage into a graph. And that worked reasonably well. So that's the process.
With the setup of our data collection system came the completion of the physical testing rig. The testing rig is made in both a simulational and an experimental capacity.
The test rig is a vacuum chamber with surface heating and subsurface cooling systems that simulates a lunar thermal environment for the experimental testing of our mock thermoelectric helical anchor prototype. To simulate the lunar surface's thermodynamic behavior, the experiment was performed in a near vacuum. To achieve this, we made a vacuum chamber with half-inch acrylic sheets. The vacuum chamber is held together with acrylic cement and 16 steel brackets with O-ring sealed bolts and is sealed with silicone. Instead of the planned bolts on top and bottom of the box, a design change was made to make the top of the box easily removable for access to the experiment. The unused holes were sealed with rubber patches and a silicone ring was put on top of the vertical acrylic sheets. Atmospheric pressure pushing in on the rubber box top created an airtight seal. The box top also had the added weight of the sandbags pushing down to squash uneven parts of the silicone ring and create a seal. The vacuum chamber was not perfectly airtight, but it held a near vacuum with the air pump constantly running. To simulate lunar soil, the box was filled with sand to a depth of 75 centimeters. Sand was chosen over other possible simulants, such as sawdust, because of its availability and known thermal properties that are similar to actual lunar soil. To simulate solar radiation, 3 250-watt heat lamps were hung 5 inches above the sand. For the 750-watt test, all 3 heat lamps were used, and for the 500-watt test, only 2 of the heat lamps were used. To simulate the temperature stabilization in actual lunar soil below a depth of 50 centimeters, we used a welding torch cooling system to run water through copper pipes in the soil to maintain a steady temperature. The cooling system was designed to keep the water at room temperature and could remove up to 1500 watts to do so. The water pumped by the cooling system was run through a copper pipe coil embedded in the sand below a depth of 50 centimeters. This system was very effective at keeping the sand at room temperature, our lunar subsurface minimum, and removing all energy added by the heat lamps to create a net zero energy in the test rig. Acrylic is already thermally insulative, but as an added measure, the outside of the box was covered in ceramic fiber insulation. Ceramic fiber and acrylic have similar thermal conductivities, but this added layer tripled the total thickness of insulation between the experiment and outside air. Important locations for the temperature sensors were chosen based on thermal simulations. Because of hardware limitations, we could only use 10 temperature sensors. The temperature sensors were buried at their respective depths as we filled the test rig with sand. To test the concept of using a heat sink inside a helical anchor to cool thermoelectric plates, we designed a mock anchor, a proof of concept model that could be tested in the test rig. The helical anchor was mocked by a steel pipe. For our test, the absence of the helical plates did not affect the performance of the radiator cylinders. Copper was chosen for all components that transferred heat due to its high thermal conductivity. For simplicity in the proof of concept model, the heat sink was designed to have 2 radiator cylinders, which function similar to radiator fins. They consist of a copper rod and copper pipe. The heat transfer block, or HTB, was a cylindrical copper block. For our test, the HTB was sized to have the thermoelectric plates at ground level, but having the HTB as a separate component from the radiator cylinders allows the thermoelectric plates to reach a heat source at any height above the surface by changing the height of the HTB. Constructing the mock helical anchor without the ability to weld was very difficult. We originally tried soldering the copper, but the pieces were too large to get to a high enough temperature with the available blowtorch. Metal brackets instead were used to attach the HTB and inner copper rod, which then rested atop the outer copper pipe in the test rig. All of this rested inside the steel pipe. We were very careful to fill the gap between the outer copper pipe and steel pipe with sand as if it had been drilled into the ground. Thermal paste was used to ensure full heat transfer on all joints. The original design used aerogel to insulate the HTB in radiator cylinders above 20 centimeters, the depth where temperature stabilization starts. However, due to shipping delays, we used ceramic fiber which was readily available. Ceramic fiber was installed in two pieces, a thin outer ring between the copper components and steel pipe, and a thick blanket on top that shielded the exposed areas of the HTB from the heat lamps. We used 4 commercially sold thermoelectric units. Circular thermoelectric plates would have been ideal, but were not available. They were connected in series, and their voltage over a known resistance was measured to determine power output. To predict the results of the experiment, we ran a thermal simulation in Fusion 360 of the test rig and mock thermoelectric helical anchor. For simplicity, nuts and bolts in the acrylic box were ignored, and contacts were defined within a tolerance of 0.1 millimeters. Also, the energy from the heat lamps was applied evenly on all the exposed portions of the sand and mock anchor with nothing lost in the vacuum. This is a very ideal scenario, but these assumptions allowed us to focus on studying the behavior of the mock anchor. The thermal loads on the test rig were as follows. Full heat on exposed surfaces in the plane below the heat lamps. All of those exposed surfaces absorb heat via radiation with appropriate material emissivity and ambient temperature set at room temperature. The cooling system maintains room temperature and may remove unlimited heat to do so, creating a net zero heat in the test rig, and the exterior insulation of the box experiences convection with still room temperature air. All thermal conductivity values are either widely accepted for materials, such as copper or acrylic, or were provided by the manufacturer.
Once everything had been set up, we got straight to work on experimentation, and with the finalization of our corresponding research paper, completed the last leg of our journey.